So one of the problems that we've been looking at, Radha, Alan, and James have also been looking at, is this thin air problem, pretty long-standing problem that we'd all like to fix. And I think they're going to tell us about their latest solution to it, which has some really cool properties that we're just really interested in. So this is some research which is sort of related to ours, and we're just really excited to have these guys talk at a PLAS seminar when we wouldn't normally be able to because they're in America. So an upside from this whole thing. James is the one who's going to give the talk. I hope that's a sufficient introduction.
Yeah, that's good. So yeah, thanks for having us here. So we're going to be talking about here Pomsets and preconditions as a model for relaxed memory. So what is a memory model? It essentially tells us what values we can read whenever we want to read something. So here I've got a bunch of writes, and the question is, what can we read at this point? Here we've got some shared locations, initially 0, some registers, and I'm showing you program order. And if you think about it here, reading 5 would be bad because that's sort of reading from the future. Reading 3 is clearly bad too, because that's reading from the past. And so those things seem unreasonable, okay? But we could potentially read either 1 or 2. That seems perfectly fine. If we put a synchronization here in the middle, then things change a little bit. So here I have a synchronization, a releasing write, and then an acquiring read. And when I do that, what's going to happen is we're actually going to hide this write of x is 1, because now it's sort of in the causal past. I can't really see it anymore. And so this is the idea of a memory model. We can model this with a partial order, which is really kind of nice. So here we've got a partial order where we just have a single order, but where there's 2 reasons for order here. There's order because we have program order combined with being on the same location. And there's also order into and out of release acquire events. And we can specify what it means for read to be sound really simply. So we need for the fulfilling write to precede the read. And we also need that there's some sort of order with every other write, either preceding the write or after the read. And depending upon how we decide to fulfill this requirement, we can get different results here. So if I order 4 before 2, I can see 2 afterwards. And if I order them the other way around, I'll be able to see the 4 afterwards. But I won't be able to see 1 in this case, because the requirement for fulfillment here would require that the other write is before it, or in this case, that will create a cycle, which is no longer a partial order, or the write must be after the read, which again would create a cycle, okay? So this is the idea of using a partial order sort of to model this notion of fulfilling reads. And I'll argue that this is very pretty. This is something we like, okay? But of course, things can get a little bit more complex. Things can go out of order in systems like this. So let's give ourselves 2 variables where I've got one thread here copying from x to y, and another thread reading y, then writing x, and copying the value at read from y into z. And here there's one more sort of element to this partial order, which is a dependency. So there's some sort of dependency, you can see a data dependency in this case, between the read of x and the write of y. And what we've got here is, in systems, the read of y on the left-hand thread and the write of x are independent. And so that means that they can be swapped around. And this does actually happen. So this reordering will happen. It happens in compilers. It also happens in hardware. And as a result, this program, of course, can also see 1 because of this reordering. So that's the effect of things happening out of order. And this is a very well-known situation with relaxed memory models. And you could just make a tiny change to this program, though, and things change quite dramatically. So I'm just going to swap 1 and replace it with R. And now I've got a very different program. Now I have something that's not just executing out of order. I've got a value that's coming completely out of thin air. There's nothing in this program that mentions 1. It's just copying from side to side. and it would be absurd if this program were to write 1. And in fact, if this program were allowed to write 1, we'd be able to invent pointers, we'd violate all sorts of security invariants. This is not something we want to allow in a memory model, besides being ridiculous. So, the partial order clearly prevents this, because look, I've got a cycle, right? So once I've got dependency, there's a cycle here, and that's great. So what about here? Well, in this case, if I, well, sorry, let me back up. I think that slide was a mistake. Sorry. I just want to say, this is very pretty, okay? This is really nice. So we're ruling out a thin air behavior just by having cycles, yeah? Okay, but let's take that program we just looked at. And, oh, I'm sorry, I remember what that slide was. This is just the control flow variant, excuse me. So what we could do with data dependencies, we can also do with control dependencies, okay? And this program, by the way, is also data race free. So if we were to allow out of thin air executions here, we'd be violating the guarantee that data race free programs have only sensible behaviors. Sorry. In any case, so this story is quite pretty, and is that it? If that were it, we'd be done. This would have been all over 20 years ago, but it's not it. So let's look at what happens when we get a slightly more complex situation. So I'm going to take that out of air program that I just had, and I'm just going to embed it in a conditional where I have a side of the conditional that I'm actually not going to execute. So I'm only going to look at executions where actually R is true or non-zero. And believe it or not, this actually can produce a write to 1 on Z. And you can see this by looking at compiler optimization. So the compiler might deduce that X and Y can only be 0 or 1 here, in which case it can put the constant in for the right. Sorry, I left one out. Then we can lift the right out once we know it's a constant. So we have that X is 1 on both sides of the conditional. We can pull it out, and we can reorder as well. And then we can inline this guy, if you like, in between, or interleave. And you can see very clearly this guy can actually produce 1. All right, so through this standard sort of sequence of compiler optimizations, this kind of execution can happen. And this is definitely a little fly in the ointment. And what's annoying here is that if I just change the unexecuted branch of the conditional, the execution changes completely. All right, so if I set this to be 2, well, of course, now I can get 0 or 2. But there's no way in heck I'm going to get 1 out of this guy anymore. And in fact, this whole line of reasoning is unsound, right? So you can't actually try and produce 1 out of this. And so what we've got is a funny situation. Here's another variant, which is to, instead of condition the execution of the true branch on R, where I know that I've read a non-zero value, I'm going to condition the execution of the branch on B, which is just some arbitrary coin flip. And here again, obviously this reasoning is unsound. I mean, there's no reason to assume that I'd be writing 1 on the left-hand side of the conditional anymore. I might have certainly read 0, right? So these kind of examples, dramatically sort of complicate the picture. So let's zoom in on these 3 examples for the moment. We've got an execution where we would expect to write 1, where we would expect to write 1. And then we've got executions where we wouldn't, okay? And if you look at the literature, you'll find that there's a bunch of memory models out there. Those that are based on existential justification tend to disallow the first 2 examples, or sorry, they get the first 2 examples right. But they tend to screw up the second one. So this OTA 4 example, where I'm basing this off a Boolean flip, doesn't work out in models based on commitment or speculation or promises. It does work out if you have stronger models based on some sort of universal quantification of all your possible futures, okay? But these models turn out to be, unfortunately, a little bit too strong in that they won't compile to the models that we're interested in an efficient way. And so what we're looking at is this sort of in between a rock and a hard place. And you might think, well, who cares? You know, UDA4 is some arbitrary thing. What does that do? God knows, who cares? But it turns out that we do need to care. So this is very similar to UDA5, which I put up here, which is from Lochbihler's 2013 study of the Java memory model. And this execution here is, according to Lochbihler, it's type correct if it declares X, Y, and R at type D. However, it has a legal execution in the JMM where they reference a C object. And this, when Lochbihler knows that type safety failed for the JMM, he had to partition the memory by type in order to get type safety to go through. Okay, but this is of course nonsense, right? So this means you have a separate heap for every type of object in your system. That's not really a realistic implementation technique. And further, Lochbihler showed that even if you have this kind of formal fix for type safety, you've still got real problems with the Java security architecture based on forging constants through this kind of mechanism. All right, so allowing things like UDA4 and UDA5 really is a problem. And the way we see this is that what's really failing here, it's a failure of compositional reasoning, right? So if I look at UDA4, you can see that each individual thread of it satisfies this invariant, which is that any write of y is 1 must be preceded by a read of x is 1. And if I wrote z is 1, then any write of x is 1 must be preceded by a read of y is 1, okay? So that's a perfectly sensible invariant. Each side satisfies it, but in these existentially based models, the whole program does not. Okay, it turns out that these things fail. We can write this in pastime temporal logic. And in the paper, we actually prove this property for UDA4. But the point here is that the whole program should satisfy this formula if each individual thread satisfies this formula. This is the basic hallmark of compositional reasoning.
Can I just interrupt a second?
Go ahead, please.
It's, I think I'm just a bit slow, but I've been going to weak memory talks for the best part of 10 years, and I've never successfully understood the problem of thin air, never mind what comes after that in the talk. And I'm getting close, but I still, in UTA3, I don't understand why you said writing 1 at the assignment Z equals R would be a problem. And yes. But R could be 1. Is that not true?
No, it can't. So look at star, the one right above, right? In star, yes, it can be 1, okay? Because in star, actually, 1 appears in the program, for example. Whereas in UTA3, star doesn't show up. So where are you, sorry, 1 does not show up. I mean, where would you get the 1?
Okay, so everything, this is a silly question, and basically everything is initialized to 0.
Yes. No, that's not a silly question at all. Yes, everything's initialized to 0. That's correct.
Okay, now I get why it can't be 1. Okay, that's good. Thank you.
Oh my God. I'm so psyched. We're getting out of thin air reasoning. All right.
I'm not saying I've understood everything yet, but I'm getting closer. So.
Well, if you understood it, you'd be in a minority of 1. So yeah. Anyway, so let's go forward here then. So let's just put these two executions side by side. In fact, zeroing in just on star and UTA4 is kind of helpful here, and you can see the difference in them. Okay, so the star here, we have this write of 1, which is independent, and therefore we don't have a dependency between the read of y and the write of x. Whereas in UTA4, there's no such independency, right? So you get a cycle. Okay. And this is the point where you have to ask yourself, is this still pretty? All right, it was pretty before it got very pretty, and now can we keep this thing pretty? And it turns out this is actually hard. There's a lot going on in doing this. There's, programmers want compositional reasoning. They want to think locally about their programs. They also want this, this guarantee that if I don't have data races, my program does the thing I expect, which is sequential consistency. And then on the other hand, you've got these implementers who want every possible compiler optimization to work. Sorry, can't quite do that for you. And the hardware implementers that want to ensure that we can implement these things efficiently on hardware. So, it turns out that this is, I think, pretty much unsolvable in an intelligible way without making some compromise. So in this paper, we've decided to make a compromise, which is that we're going to give up on architectures that are not multi-copy atomic. The reason for this is that multi-copy atomic architectures have become dominant. So ARM has recently adopted them, so has RISC. So all of the major players, except Power, are all adopting this model. And the advantage here is that we can simplify how we think about our model by, in fact, using a single order. The use of a single order is supported in hardware. So what do you give up? Well, you give up some sort of funny distributed systems behavior where writes are received at different threads in different orders. Okay, but if you're happy to accept the idea that a microprocessor is not a distributed system, then we're good. Okay, so in any case, we're going to limit attention to this type of architecture. All right. People have been working on this problem for a very long time. I'd say this really started off in 1999 when Pew noticed that common subexpression elimination failed in the JMM, and that resulted in the JMM and then its children. There's also these strong models which have sort of the reverse properties. They behave the way you expect. They're good for programmers, but they're bad for implementers. And these include the sequential consistency itself and some other models. And you can see our work here at both ends of this in 2010 and 2016. And there's been other approaches as well. There's operational models where you include compiler rewrites actually as part of the operational semantics. And there's symbolic executions where you get a bunch of orders out of those symbolic executions, and you determine acyclicity requirements on those. And quite prominently Mark's C11 model. And then there's been some follow-up on the event structures stuff that's making it not so strong, including the paper that Mark and you guys recently put together for ESOP. So that's all great. So where are we going to go here? Well, I'm going to be guided by just a few principles. So the first one is indeed compositionality. I want compositionality in the construction of the semantics. So we're going to do a denotational semantics. I also want compositionality in terms of how I reason about the resulting semantics. I want to be able to reason locally about races. I want to reason about safety properties compositionally in the way we just did for UDA4. Another principle here is going to be that we're going to glue everything together with logic. In particular, we're going to use logic to specify safety properties for this compositionality. We're also going to use logic while putting together or constructing these things by using preconditions inside of these Pomsets. And finally, we want one order, not two. So we did a version of this with two orders, and I still don't understand it. Anyway, so one order, not two. And I'm going to explain this all to you in 4 slides. All right. So a Pomset is what you expect. The only thing I'm going to do here is put formula on these Pomsets in addition to action labels like reads and writes that we've been seeing. We'll make a consistency requirement for these formula. So the conjunction of all these formula should be satisfiable, and we'll somehow relate the formula to the order. Then we have the notion of fulfillment that I already told you about. So there's 2 requirements. The write must precede the read, and all the other writes have to be ordered somehow. And we can say that a POMSET is closed on X if every read of X is fulfilled and every formula is independent of X. All right, so there's some definitions. I'm just going to define a few operators, and then I'll give you the semantics. So the first one is restriction. So restriction just takes the subset of the set P, where each element is closed on X. The restriction here, or the filter here, is going to ensure that we just take POMSETs from script P that are strong enough to imply phi. We have a substitution, which is going to substitute through formula. We have parallel composition, which is allowing us to take elements. It's essentially union, except that I can collapse elements on two sides. And if I do collapse elements on two sides, I take the disjunction of their formula. And finally, we have one kind of, okay, fine. It's big, right? So this is prefixing, but you can just zero in for now on a couple pieces of it. So prefixing introduces a new action, and the new action has some sort of constraints on the formula and the order, okay? So in terms of how it falls in, I'll walk through that through examples. So this is then the semantics of the language, yay. And the semantics uses all of the operators that we would expect. So we have a termination condition, that's the tick. And then we're using substitution through here. We're using prefixing. We're using the filtering operation. We're using parallel composition. We're using restriction. And I'm going to include in here both memory access operations, register access, and fences. And these things have annotations to indicate their memory order properties. So we'll have relaxed, release, acquire, and sequentially consistent memory access. And for fences, we'll have release fences, acquire fences, and sequentially consistent fences. Okay, so that's it. That's the whole language. And by the way, I didn't leave anything out. That's all the definitions you need. There's no secrets. There's nothing hidden under the table. That's the whole thing. All right, so I just want to walk through an example, that star example that we had, and look at how we calculate the dependencies in that example. So here is a POMSET where I'm writing 0 into Z, and we're preconditioning that on the fact that R is 0. So if I instead write 1, well, then I have to have the precondition that R is 1. If I write 2, it should be 2. All right. If I prepend 2 of these guys together, I might end up with 2 events. Okay, so we have the possibility, of course, reading and writing 0, reading and writing 1. Now, these things are calculated independently, so we could end up with some trouble if we had inconsistent choices. So this is ruled out by the consistency requirement for POMSETs. So we won't, if we're using the same register twice, we'll need to be consistent about what we think about it. So here's a separate program that writes X is 1. And what I can do then is put some control around those. And when I add control in here, what I'm going to do is simply strengthen the preconditions to have the predicate. Then I can simplify these. And now it's quite obvious if I put them in composition, I can collapse or coalesce X is 1 from both sides. And when I do that, I get the disjunction of these. So in other words, this if then else can produce X is 1 either when R is 1 or when R is 0. Okay, if it wants to write Z is 1, then we need to have that R is 1. Pretty good. Okay, note that if we put a 2 in here, we'd end up with a different situation, because in that case, I would not be able to coalesce these events. And in fact, this Pomset is inconsistent, so we wouldn't allow this at all. Okay, so at this point, you'd have to pick the left or the right. You can't combine them in any way. All right, so let's start fresh here. We have this program, and now I'm just going to embed it in the rest of the term. So given that, we can first precede this with the read of y. That's going to perform a substitution. So we substitute the r's with y's here. Then we can actually add the event. So when we add the event, we're going to add a bunch of conditions, which is that the preconditions must be consistent with the value that I just read. Okay, so that in addition having y is 1 or y is 0, now I have 1 is 1 or 1 is 0. Okay, that's just substituting the value I just saw. So that's great. And note that this makes it so that incompatible reads are just going to be disallowed, right? If you read something that's not what you expect, this becomes inconsistent. Okay. So the other thing we can do here, this is optional, is to introduce order between a read and a write. And when we do introduce such order, we can actually substitute the value that we've read through for the variable. So this will actually simplify this. So now I have simply a tautology here for z. All right, so given that, we can then prepend a write. And when I prepend a write, I can also, I'm actually going to do a substitution of the value written for the variable y. And here we can actually do the substitution through for the occurrences of y that appeared for this write XX action. Okay, so what we've got, and this is kind of interesting, is we've got preconditions here for write x1 and write z1. They're actually fulfilled from different places or satisfied from different places. So the precondition of write x1 is satisfied by the write of y, and the precondition of z is satisfied by the read of y. Note that the reads impose order, whereas the local writes do not. All right, if we simplify everything down, we end up with this. So we've got a nice, simple little meaning for this program. And we can then start thinking about what happens in the concurrent semantics, where we have to worry about writes and fulfilling all the writes. So the first thing is we have to order conflicting accesses. So we'll have an order here from the write of y to the read of y. And we need to have initialization for x, so we'll throw that in. And then we'll introduce this other thread, which is copying x into y. And so there it is. And at this point, then we have to fulfill the reads. So in order to fulfill the reads, we can do that by adding in the appropriate order. And once we've done this, yay, we've got the execution that we started for star. Okay. It's really okay because it's a partial order. All the reads are fulfilled. All the preconditions are tautologies. That's an execution. If we change this to O to 3 instead, this is going to be disallowed because it's not a partial order. All right, dealing with synchronization is really not that hard. So all we need to do is have a few axioms which say that if I'm prepending an acquire and I have an old release, well, then I introduce order and a few things like this. Okay, these are sufficient to get us what we need. So here's a simple example where I'm publishing one to another thread. So similar to my introductory example. And all it does is introduce this order. The releasing write introduces order from the write of x to the write of y. And the acquiring read introduces order from the read to the subsequent read of x. Okay, and fences behave as you would expect. The language allows buffering examples the way you expect. In fact, all the litmus tests sort of work the way you expect with one or two maybe exceptions, which I'll talk about. Here is how store buffering works. This is how load buffering works. The interesting thing about this semantics is how well it deals with the concept of what's known as internal reads. So I ask you to look at test case 1 here. This is test case 1 from Pew's causality test cases for the Java memory model. And you can see here that what I've got is you know, very simple looking program, but its semantics is quite complex. What I'm doing here is reading X, and then if the value I read is positive, I'll write Y, and then the other thread simply copies. And you can see that the way this works out in our semantics is that this, the precondition on the right of Y is actually ends up being satisfied by the local initialization. Right? That's going to actually cause the substitution through to get that fulfilled. There's more test cases like this. There's, sorry, there we go. Internal reads play with synchronization. The SC fences behave just right. They do all the right things. Coherence works more or less the way you expect. And we end up with what's called local data race freedom here as well. Okay, so races from the past can't screw up the future. So this is an attempt to read 2 values from an old race, and this is not allowed because of you'll get cycles. You also can't see races from the future, where the future here is defined as the fenced off future. So you can, of course, have time. This is a denotational semantics with the notion of time here is about causal time. It's not about wall clock time. But in causal time, you can't see from the causal future. There's a lot of transformations that this validates. So we get all the reorderings you expect, write to write, read to read, write to read. We get Roach Motel both ways for release and for acquire and release. We get redundant fence elimination, redundant read elimination, irrelevant read elimination. And one thing I'll just point out is that irrelevant read elimination is actually not sound in the model I've shown you so far, because whenever I insert a read, I'm always adding a read event. So in order to do this, there's a little bit of extra work, which you can see in the paper. The same thing is true for removing writes. So we have store forwarding and dead store elimination in the paper. There's also common subexpression elimination works here. We have dead code elimination. We have code lifting, lifted out of a condition. And we do have a little bit of extra work for case analysis. So to allow a program to be refined by analyzing possible cases. We also get scope extrusion. So all these kind of algebraic properties you might expect. There's other transformations. Some are true. Sorry, there we go. So some are true, but we don't have a proof, such as redundant right after read elimination. Some of these are observationally sound in our model, but they're not actually valid in the model itself. So we'd have to do some more fiddling around with getting rid of redundant actions and things like that. So there's access mode strengthening, commuting or eliminating some synchronization actions, implementing synchronizations using fences, implementing locks using synchronizations. And there are some things that are observationally sound in some contexts, such as access mode weakening or lock elision, which we haven't addressed here. And there's some things that just aren't sound. So thread inlining, relevant read introduction, write introduction, these are just not sound, period, the end. Other results in the paper, we have that it compiles efficiently to ARM. We have a local data race freedom result. And the limitations here are we didn't deal with loops or functions. We didn't do proper sequential composition. We've only prefixed one action at a time. And we didn't deal with mixed sized access. We haven't dealt with all optimizations. The logic we have for out of thin air is quite weak. So it's enough to get us ODA 4. So we can prove that can't happen, but there's other ODA examples that I can't prove with that logic. And we are, of course, working on MCA. So that's good for most major architectures, but not for power. And we didn't separate address dependencies from other dependencies. And that has some implications for things like Java final field semantics and things like that. Okay, so that's it. Let me just remind you what we did. We started with some principles here, and those were compositionality. We wanted to be compositional in construction and also in how we think about the programs. And we thought about the programs using logic, both to build them up and to check their properties after the fact. And we did this all with one order. That's it. Thank you.
We'll do applause.
And we have Alan and Rada here too, if you want to ask questions. Yeah.
So are there any questions from anyone?
I have one. I don't know if I'm close enough to the microphone to be audible.
Can you hear Dan?
Oh, hello.
Yes.
Good. So I actually have a question about how you maintain compositionality when you're doing this substitution operation inside your little conditions on your events. So could you just go back to the slide where you work through star really quickly so that I can point out where I'm confused?
So somewhere in the past or in the future?
In the past.
All right. All right, so that I don't think I've done a substitution yet. So the substitutions, oh, so it's happening after the
Yeah, there we go. Right. So
yeah. The substitution I think is going to happen on the next slide. Here we go. Let's start. There we go. That's the first substitution. There we go.
all right. So now that you've performed this substitution and you are very definitely declaring here that that you are looking at the contents of Y here and not the contents of R, and then later you precompose another write which does another substitution and says, I've now written to Y and I know what this value is. How do you handle a situation where you want to stay compositional and my context is going to be, I'm going to have another thread which is running concurrently which also writes to Y, and I want to know that I can still access, say, the false branch of this, which is now no longer looking at the value of Y, but looking at the value that you've written to Y.
So yeah, I'm not sure I totally understood everything you asked, but let me point out one thing and maybe it answers what you're saying. So these preconditions are visible sequentially. They're not visible concurrently.
Okay.
So if you're going to fulfill a precondition, it must be from prefixing. That is the only way to do it.
Okay, so if you did want to sort of get rid of that prefixed write and instead have it happen in another thread, what would that look like? Would you still have the version of the...
You wouldn't, no, this wouldn't happen. Yeah, you couldn't do it. Yeah, you wouldn't be able to, so you'd actually have a dependency. If this local write was not here,
yeah,
then you would have to have a dependency from this read in here. In fact, you couldn't be reading 0, you'd need to be reading 1, right? So you'd have to have something to fulfill it. Because you have these two constraints, which is fulfillment of reads, and then you need to have your preconditions all become tautological.
Okay, and if you don't have a tautological precondition, then you just write down that we've got this dependency here, yeah?
Yes, yes. Once you've got dependency, that can't go away. So if you use a dependency to remove or to make a precondition tautological, then the dependency is stuck there forever.
Okay, yeah, that clears it up. Thank you.
Yeah.
A question? And I have a question. You're using one order and insisting on multi-copy atomicity because that it allows you to have one order. And I see how much you get from that. It's a really pretty semantics for one of these thin air things, but we really don't want to have to suffer multi-copy atomicity.
Yeah, you just need 2 orders.
You can do it with 2 otherwise. That's your
well, this is speculation. Okay, so we actually tried this in the first round of this. So the first round of this model was ended up in S&P, and it was mostly focused on microarchitectures. So we didn't prove any of the properties like compilation ARM or all these compiler optimizations. We didn't do any of that stuff. But we were sort of thinking about that. And at the time, we were thinking not to be restricted to MCA. So we did have 2 orders there. But it didn't work. In the end, that model, once I followed through on it, it wouldn't compile to the IMM, for example.
Yeah.
So
I guess I have a question on that topic, which is, do the optimizations or the kind of refinements of the predicates that you've got rely on having a single order? Do you get additional optimizations validated because you've got a single order, or is it all thread local?
Yeah, it's all thread local. They really are. I mean, this is really 2 papers slapped together. One of them is about how to calculate preconditions, and the other one is how to leverage MCA.
Okay.
And so you can take the lessons of one part without the other.
Yes.
Yeah. So I actually have, I have thoughts, and I have thought through what I think you need to do in order to get non-MCA allowed. And there's, I mean, you can see in the end of this paper, I sort of sketched what we did in the S&P paper. It's in a footnote there, but it's very similar. Just in that S&P paper, we required a kind of relationship between weak order and strong order, kind of semi-transitivity. We're going for 3-valued Pomsets. And it turns out that those requirements were too strong. So in order to get what you need, you can't have that kind of 3-value Pomset thing. It needs to be a weaker connection between the 2 orders. Okay. But the ones we identified as being weakened are the ones you need to weaken. It's actually in 2 places. It's in the second part of fulfillment. Actually, I can show you right here on this slide. Let's get fulfillment up. Yeah, so this second condition of fulfillment, you need to weaken there. And over here, when P5B, when D and E are conflicting actions, you don't want that to be strong order, you want that to be weak order. So it's those 2. If you just change those 2 and then fix it up, should be good. Yeah.
Thank you.
James, can I add one comment?
Yes, you may.
Okay, so I just say, I think, we should point out that one modern architecture trend which we are unable to capture in our current model is the sort of which is a distributed system, is the NVIDIA family. Okay, so
we're particularly interested in that ourselves.
Yeah, it's and so there, if one is thinking, I mean, yeah, okay, fair enough. I mean, let me leave it at that. Yeah, just I want to just say that. Yeah, it's that is a distributed system in in the sense that it's not permitted by MCA. So.
Yes, absolutely. No,
yeah.
it's
the only way you don't support NVIDIA systems. Is it just because it's non-multi-copy atomic?
Yeah.
That makes sense.
Yeah, I mean.
Yeah, I'll put in my little bit about this, which is related to both of those 2 questions, which is that my kind of like informal hand-wavy way of thinking about this is that in this model and in MCA, there's 2 ways that locations are accessed. They're either accessed internally or externally. So when you've got a read of X, it either gets threaded through the preconditions, and you use substitution as a way of dealing with it, but pretty much like you would for Hoare logic, because that's the kind of like the model where everything thinks it's single threaded, or a read might be an external read, in which case it puts down a read action, and there must be a fulfilling write action for it. And the thing that MCA allows you to do is it allows you to partition every read that way. So every read, like, it's got its way that it handles preconditions, its way it handles internal reads, and it's got its way that it handles external reads. And those nicely partition, and moreover, they play well with the orders, so that when you've got causality, coherence, that contributes to the global order, and that everybody agrees about the external actions. So it's the fact that you can partition the world into just the thing that happened internally and just the things that happen externally, and they all agree. That's the thing which makes this model fly, and it's like the thing that MCA is giving you. But like I said, that's the hand wavy version of it.
Are there any other questions out there? Okay. I guess we should thank our speakers then.
More digital applause.
More digital applause. Yeah, why not? Eh?
All right.
Thank you for doing
Thanks,
this.
guys. Yeah, no, thanks for inviting me. I thought it was awesome. Yeah, in fact, now that we realize that we don't have to get on a plane to talk to each other, we could chat more about this. Yeah, if in particular, if you're interested in pursuing this idea with non-MCA architectures, I think we'd definitely be interested in chatting about that with you, because I don't think it's something we're going to pursue necessarily ourselves. So
we have told the funders that we will pursue this. So we will be pursuing this, and we would love to talk to you in some more detail about it. We've got lots of angles on it when you start to add in other kinds of optimizations on on addresses and things. Yeah, we've been talking to the